We will now proceed with the next plenary lecture. Our next speaker is Sir Konstantin Novoselov, and the topic that he'll be sharing today would be materials for the future. The Q&A session will be moderated by Dr. Yang Le. Let's welcome Sir Konstantin, please.
Do you go straight? Or? Okay, so good afternoon, everyone. So it's really a pleasure to be here, and it's well, over the last 3 days, and it's really an exciting opportunity for everyone, not only for you, but also for ourselves to interact and try to present something for general audience. I presume there are not that many, hopefully not that many experts who are going to criticize our recent work. So I can tell you not completely true story now. Just so just make it nice and beautiful pictures. Anyway, so I'll try to talk a bit about the work which we do now. How do we see the future of material research? I'm a physicist by training, but increasingly I work on materials, and well, we'll just I'll try to structure the presentation in two parts. So what do we have right now, and how can we go, and what can we expect from this area in the future? So, and the easiest way, surprise, is to start with graphene. I'm sure that many of you do know this material. It's the thinnest possible material. It's actually a very simple material as well, consists only of carbon atoms in a two-dimensional setting in a honeycomb lattice, but yet it's actually the same this very lattice, which gives it very interesting properties, because the honeycomb lattice it's actually not one of those simple Bravais lattices. It has 2 atoms per unit cell. So a lattice, a crystal, is something when you take an atom or a unit cell, and then you can replicate it in space simply by translating it by certain unit vectors. So here, graphene, actually, you need 2 atoms. So here I colored them red and green, even though we all know that carbon atoms are blue, of course. And then you need 2 of them to create a honeycomb lattice, which gives, and then you need to quantum mechanically allow your electron to sit on both atoms simultaneously, which gives you this so-called bonding anti-bonding state, which results in the famous Dirac-Cohen's linear dispersion relations, which you usually observe only for relativistic particles. So I'm not going to go into details, into equations and so on. Just give you one example. What kind of unusual properties can you expect from such a material? Like many of you would realize that if you run a car into a wall, you would most probably crash it, right? So that's the common wisdom. Now, in quantum mechanics, there is an effect called tunneling, quantum tunneling, which gives you a tiny probability to go through this wall. So the probability is very tiny. Don't try it neither with Mercedes nor with Volkswagen. Really doesn't matter. So it's pretty much 0 for the non-quantum object, but actually in electronic world we deal with this quantum tunneling all the time, and it's really one of the biggest problem for modern transistors. As transistors become smaller and smaller, quantum tunneling gives you a lot of leakage current, so that's why your microprocessors overheat all the time. Now, for relativistic particles, and including those electrons in graphene, the situation is such that you can go through this wall without any problem with 100% probability. It's something which we see in our experiments every day. So it just shows how unusual the electronic properties and optical and many other properties of this material are, and that's the reason why lots of people work on it, including those who try to use it for electronics, for optoelectronics, and so on. So, and generally, there are many other unique properties with this material. It's the thinnest possible material, the stretchable, the most impermeable, conductive, thermally conductive, so on, so on, so on. And then that's the reason why it has been used and tested for many different applications, from energy to composites, from sensor to printable electronic. So, but before I go into the applications, just let me, and promising you what's kind of graphene world you will see in the future, let me just give you a few examples of what graphene has done for us already. One thing, it created workplaces, quite a lot actually, and some of our students opened some spin-off companies, and some become rich, some become poor actually with those. But so it was meant as a joke, but until a few years ago I received my regular copy of the Glamour magazine, and on one of the pages you read 5 jobs our kids will be doing, and it's right next to virtual architect, avatar stylist, and active makeup developer. There is a graphene engineer. So if said by Glamour, must be true, right? So then it also provides entertainment. I'm sure that in this audience I don't need to advertise this sitcom, and so for those who don't know, The Big Bang Theory, so they discontinued this, but it was very popular sitcom about 4 postdocs from Caltech who were just one of them, the main character, probably the string theorist Sheldon, and then in one of the episodes alone, he was trying to figure out why electrons in graphene behave as massless quasi-relativistic particles. You all know this already. It's because of the honeycomb lattice. It took him the whole episode because some of the formulas on those whiteboards are actually wrong. So that's they are for bilayer graphene, they're not for monolayer graphene. So, and then, so it also gives shout, if you ever fancy to go and live in Tallahassee, Florida, you can live on graphene lane there. But generally, so when coming to applications, surprisingly, I mean, for us, graphene is very special material. When it goes to application, it follows the footstep of pretty much every single advanced material before it. So it starts from the composite materials, where you can ask huge premium for tiny improvement of the properties. So usually in the sport goods, ourselves we collaborated with McLaren and Richard Miller to create this world lightest, unfortunately world most expensive watch, definitely most expensive per gram. It's 1 million Swiss per 32 grams, but well, it works. If you haven't got 1 million Swiss, you can spend $250,000 on this car, and this is becoming real. So it's a small manufacturer nearby Liverpool, and they produce these BAC mono cars, and they use graphene panels for their composites, not for the sake of the lightness or the strength, but primarily because of the thermal conductivity, which gives you faster production rate. And then, but you don't actually need to go for those. So these days, every single Ford car would use graphene under its bonnet, again for some strange noise canceling, noise absorption properties. So, and then if you go for electronics, again, every single Huawei phone would use graphene for thermal management. No any other material can give you more than 1,000 meter Kelvin thermal conductivity. And then I don't want to go into details into electronics and optoelectronics, which is becoming quite popular and being developed right now. So for some time there was a question about the production of this material, because we started a long time ago with so-called Scotch tape method. You basically take a piece of graphite and cleave it with Scotch tape. And I should admit we still use it. We still use the same method up to now in our labs. Just Scotch becomes slightly better, but that's it. So just still the same method. But for the industrial production, there are many other ways how to produce graphene. Say for electronic grades, you would use CVD, chemical vapor deposition, where you run carbon-containing gas on top of a surface of a hot metal, and then this gas cracks on the surface, hydrogen flies away. It's a way to produce hydrogen, actually, and then carbon rearranges itself in graphene. And the beauty of this method is that you can use pretty much anything, any carbon-containing species. So, for example, when we needed to produce iron-doped graphene, so for some quantum measurements, what you do, you just use this. You simply prick your finger, spread it on copper, stick it into the furnace, and that's it. So you got your graphene. So for anyone looking for a job, so we still hiring for these sort of experiments, but don't worry, those fingers are mine. So no students were hurt during those experiments. Anyway, and there are a few other ways as well how to produce this material. But then the story continues when you say, look, if you get such interesting results simply using your lead pencils, if you invest a little bit and buy some other pencils, can you do something else? The answer is yes, you can. So you can actually produce many other two-dimensional materials, and these days there are so many of them. There are many dozens of them, and they cover a huge range of properties, from, say, the most insulating to the most conductive, ferromagnetic, superconductors, so just anything you want. And that actually gives us a very unique opportunity. Just let me step aside a little bit from my story and just try to explain you what kind of and why do we need those opportunities. So generally, of course, materials are extremely important for us. We even call the ages we live in by the names of the dominant materials, right? The Stone Age, the Iron Age, the Bronze Age. The good question is which age do we live in now? And it's probably for the first time that we have a choice now, right? You can call it a digital age or silicon or maybe even nuclear if you want. So we have a choice, and probably we need to really to make a very smart choice. So we start to get quite a diversity in and adaptivity in terms of custom engineering. So we can draw something on a piece of paper or on your computer and then 3D print it immediately. Or we start to do it. We start to do the same with chemicals as well, right? So you can order DNAs really just from your office, and then a few weeks later you will receive it in a vial. Now, can we do the same with materials as well? So why would we need it? So here is an example from electronic technology. So the electronic technology stick with one material, silicon, for more than for 70 years now, right? So, and in principle, everything was going quite well. So it's a very simple, very robust technology. So we can produce very interesting structures which actually do work, and that's great. So, and it was indeed very simple until 1990. So those are the elements which we use in silicon technology. So it's silicon, boron, phosphorus for doping, right? Aluminium for interconnects, hydrogen, oxygen for passivation. Very, very, very basic technology. So then after 1990, we needed more denser transistors. We have to have better interconnects. So we used copper. You start to use copper, you need some diffusion barriers, work function matching materials, but still manageable technology. So these days, because we stick with one material and we keep adapting and changing it to the new requirements, we use more than half of the periodic table for our silicon technology. So it's actually quite bizarre, because if you compare how many materials, how many elements can you find in your body, there are more elements which we use in silicon technology than you find in your own body. And you would agree with me that human body is much more versatile and adaptive than modern electronics. So, and that's generally the case. We really still from the Stone Age, we use only few materials, surprisingly few materials in our technology. So all our electronics is silicon. Construction, we depend on the strength of steel, really, for aerospace, aluminum, until recently. So we basically become slaves of those materials. So we just, if you want to make something, to create a new device, the engineer should first check, was the silicon bandgap, was the work function of silicon, was the bandgap of silicon oxide, and then design this device within those constraints. Ideally, of course, you don't want this. You want to design freely and then find a suitable material for it. And we do this with the so-called composite materials or heterostructures, and they do indeed exist. We do use it, but only really few and far between. Ideally, you would like to have this opportunity to build materials by atom, or at least layer by layer engineering, and then program, okay, I want my top layer to be a sensor, then to be like a power supply, the next few layers, a logic or interconnects or whatever. And now we have this opportunity with the 2D materials, because when I come to lab, I have all those one atom thick crystals available to me. So what I can do now, of course, we study their properties individually, but what I can also do, I can combine them in a manner Mother Nature never intended it to be, and then I can create really new structures. So we call them van der Waals heterostructures, and I really can program their properties with very, very high, with atomic precision and with fantastic flexibility, because I have so many of those materials. And indeed, many new devices, many new physical effects have been demonstrated with those. So this is probably one of the most complex material which we created, but then you just apply voltage and then it gives you light in return. So it's an LED, and because we have so many of them, so we have we can change parameters in a wide range. Now, just to show you one example how versatile is technology, so and how flexible and how tunable is this technology. So of course we can choose the type of material which we sequence. So one layer of this, two layers of this, one layer of another, three layers of that. But then we can also control even the rotation between them. So you just put two layers together, and then if you start to rotate, you form this so-called Moira pattern, and that by itself changes the properties of the resulting structures dramatically. For example, this way people manage to get the results from Pablo from MIT. People managed to get superconductivity in carbon materials, or insulating insulators, mod insulators in semiconductors. So it's really there is fantastic versatility and tunability of this technology. So I don't want to go into details on this, but we can make it ferromagnetic just by rotation, for example. So really very just quite a few knobs we have. So this is basically the current status of material science, that we start to move from the existing materials, from relying on the existing materials only, to tailored materials, to custom materials. So we can control their properties, we can design those materials on the atomic scale, and we can tune their properties for specific applications. But let me now try to look a little bit into the future and ask ourselves, if we are allowed to dream about any materials we want, what kind of materials we actually want? So I know what we can create, but what do we actually want? And so let me share with you not my dreams, but the dreams of the directors of this movie. So I'm sure that many of you recognize it's Terminator 2, right? So the movie was shot in '91, and the plot is that the robot, I guess not many people actually seen the movie. So the robot from the future, and the future was set in 2029 for them, was sent back to '91 to kill Sarah Connor and her son, right? And I'm only showing it to you because I want you to see how people in '91 dreamt about future material. So it needs to be flexible, adjustable, I don't know, liquid metal, so be self-repair, so changing color, changing shape. So now we are, so I should apologize so we are in 2023, and I guess you would agree that unfortunately we are a bit far away from that dream. And frankly, the worst part is that if we continue on the same path, we will never come in 2029. We will never come to those robots ever. And the reason is not just that it's the problem with the robotics. It's generally our technology is very much top down. So it means that individual components in our technologies, they are not functional. So the functionality only comes when you assemble them into a system. So you basically focus all the functionality only on the system level. And that's the reason why our silicon technology is so complex. So you basically just put everything, you put all the functionality on one level. Biologic, and it's true not only about clockworking or robotics, or all our systems are the same. Now, biological systems actually operate on a completely different principle. There, the functionality is spread across different levels, right? So individual proteins, they're functional. So the individual membranes in the cells, organs, and so on. We don't think. So we don't control, okay, we need this protein to unfold, just catalyze something, then fold back, and so on. It is done somehow by itself, so it is the internal properties of those structures. And that's actually what we would really like to see. We would like to move some of the functionality from the system level to the material level. Let's make our materials to functional and intelligent by themselves. And now, for some reason, I have a bit of a problem with my computer, which I really don't understand why. Sorry, guys. I might have to actually close it and start again. So So how do we do it? How can we create materials which are functional in their own rights, and so they can perform certain functions without being controlled from outside world. So just let me Try to connect again. Can you see it? Okay, so we try to invent those functional intelligent material. Functional means that they can be programmed to do certain work depending on the particular conditions. And intelligence, well, there are many definitions of intelligence, but let's say the simplest one, that they have memory, so they can learn something. So just one example. For some time, so people have been playing with graphene membranes, for example, for water desalination, for gas exploration, and so on. In Singapore, 100% of water comes from desalination through those membranes, not graphene, but some membranes. But okay, imagine even if you have the best membrane ever, you still need to control its quality. You still need to put some sensor into the stream, and then you would this sensor sends a signal to the computer. Computer analyzes it, sends a signal to the actuator, which closes or opens the valve. But imagine that you can drop all those functions into the material itself, into the membrane itself. If you make it functional, it can change its properties depending on the particular species it sees, and then just open or close depending on the conditions. So you basically put the sensor, the actuator, and the analyzer functions into the material. Then there are a few other examples as well. I won't go into those now. So the idea is great. The problem is that if you try to make materials with memory and functional, it means that they would necessarily be out of equilibrium, and that's what physics doesn't really know how to do. So we're really bad with the out of equilibrium system. So all our experience is only with the in equilibrium materials, in equilibrium systems, and then if you want to do something out of equilibrium, you can a little bit add some perturbation theory, and then try to study those properties. So we're really bad at predicting those dynamic properties. So what do? The only we can actually guess how those materials should look like. Well, we know that they need to be probably composite, and with the strong interaction between the components, but also that there should be some multiple interaction between those components. And then if you do this, you create so-called degenerate energy landscape. So there are many energy levels which are close to each other, and then you can navigate a pathway which is almost adiabatic, and then you can create some useful function and return to the original state. So it's not a new idea. That's exactly how proteins in our body work. So they have many possible folding stages and states, and those states, they correspond to different functionalities, but then there are pathways how to fold and then return back so to unfold, and how to return back into the folded state. So that's exactly what we do. We try to use it on the material level. So we utilize different components of different load dimensionality. We try not to work with the three-dimensional materials because it's very difficult to change the bulk, and we really need to be able to change the internal properties of the material. So we need to make this material, this composite material, to be responsive for a particular stimuli with a certain response, but also change its internal structures, have a phase transition inside. So we basically, what we do, we engineer multiple numbers of the phase transitions, and then you can make it functional, programmable, but also you can program memory function inside of those materials as well. So as I said, it's actually very difficult to do it with the traditional physical formalism. So we increasingly use machine learning, and in particular dynamic machine learning here. And of course, you have to use to create big data through the robotic labs. So this is just, so here is an example of a student robotic lab. So just a very basic approach. You take a video how your student work and then create a lab which mimics the behavior of the students. It works, but in reality, the real robotics labs, they're much less versatile. So the real labs, so they're not, of course, they don't look like this. You actually have to you actually have to properly design a robot for a particular function. So we have robots to measure membranes. We have robots to measure drug delivery systems. So they synthesize, they measure them in the same setup. So we don't need actually robots which move around and use their arms and try to open the bottles. So, but here is an example of such a dynamic machine learning. So we create machine learning to learn the behavior of the folded and unfolded polymer chains. It's not exactly proteins yet, so there is no charge here, but it's a basic polymer. But basically through observing the behavior of those proteins, so of those polymers, the neural network, if you give it a little bit of the knowledge about physics, so here we just gave it only the Onsager relation, then it can predict the folding and unfolding trajectories, how many knots or just how many folds would you get if you apply certain force to it. So it can predict it very well. So those protein folding is not the only dynamic problem which we would like to solve. So here is another example of a dynamic material. So this is now the high entropy alloy, which was programmed to have the self-healing property, for example. So you basically drill a hole in it and then give it a little bit of energy, and then you can program to self-heal and close this hole entirely. So clearly very out of equilibrium material, but it can be programmed to perform certain function. So here is another example of the out of equilibrium. I'm not sure if you can call it material, but definitely composite. So you can think about it as a biological fuel cell. You basically combine bacteria with metal form. So in this case, it was we either use graphene form, or it's even better if you use metal polymer, and you can you choose those bacteria which can emit electron during their life cycle. Then you can collect this electron and use it in the external circuit. You basically start with one bacteria, some monomers, you add some sugar or lactose. Those electrons help to polymerize your conductive network, and then at the end you get a battery which you only need to feed sugar, and then you get electrons into your external circuit. So that's the way how those bacteria look on the graphene network. And I should say there are many other examples of this. So we're trying to create smart drug delivery, which can be programmed to open a capsule, which can be open and closed under certain conditions. So the reason why we cannot take just a pill with the COVID vaccine is because those vesicles, they're not stable under low pH. If you can close it in low pH of your stomach and then program it to open in your bloodstream, you would solve this sort of problem. Or those functional materials can be used on much larger scale as well. So actuators which can be programmed to respond to different humidity, light of different color or different temperature, and so on. So I think I will probably stop here just to say that. So I showed you two stages in material science. So currently we start to work on the custom tailored materials which we can design for specific properties. But really we don't want properties, we want functionalities, we want dynamic materials which can think on their own and which can change their properties depending on the external conditions, and maybe even learn from those and make decision on their own. Thanks a lot. Sorry for the problems with the computer. It's really a pleasure to present to you. Thank you.
Thank you, Sir Konstantin. We invite Dr. Yang to moderate the Q&A.
Thank you, Konstantin, for a very insightful, interesting conversation lecture that we've just heard. So I'm Le from IMRI, the Institute of Materials Research and Engineering of A*STAR. So I'll try to aid this discussion along. So we have many physical audience here. So I've already seen there are people lining up for questions. You can introduce yourself and then followed by the question. And for our online audiences who are tuning in, please feel free to type in your questions on the online platform, and we will, if the time permits, we will get through those as well. Yes, please. Yeah.
Hi, thank you for this wonderful talk. I'm Noemi from University of Cambridge in the UK. I just wanted to know, so humans and living beings are the produce of virtually millions of years of evolution. And so I just wanted to know if you had like a wild guess into, how long will it take to get the next Terminator, like in real life?
I guess no one really needs a Terminator, otherwise it will have been created already. Maybe people are scared of those. But I think the dynamic problems and those devices which can live their own life and change their behavior depending on particular parameters, I think it's actually quite close. It's definitely so we definitely understand quite a lot about, well, much more about intelligence, though definitely not everything. So we definitely learned about it quite a lot with the use of AI. I mean, I'm outside of this area, but I'm becoming a great user and maybe even believer into this system, into this technology. So I think we will see those functional materials getting into our life more and more. Of course, we don't really understand how life works, and why and what really the evolutionary pressure. We tell those stories and we think we understand, but I'm afraid the situation is much more complex than that. When we design those materials, we probably don't need to learn entirely from biology. So we don't need to utilize the same evolutionary pressure on our materials. So we can make it playing by our own rules, by way simpler rules. So if they're simpler, you can probably it will be easier to control.
Thank you.
Thank you. Thanks as well. So the gentleman here, please.
This is Philip Closer from the University of Cambridge. Before graphene, there were carbon nanotubes. I myself work on carbon nanotubes. Can you maybe comment on the role of one-dimensional materials versus two-dimensional materials in the future?
Sorry, again, the question is whether there is any future for one-dimensional materials.
Yes, because the hype has died down and has been mostly replaced by two-dimensional materials.
I mean, I don't really. I'm a physicist, so I naturally prefer two dimensions because it just gives you a little bit of more room to play, but less than in three. So you get some interesting topological properties. But in terms of, I don't think you can choose materials simply by the dimensionality. So there is so much interest in physics in carbon nanotubes. I don't think one-dimensional materials are better or worse. Even coming to applications. So these days, both graphene and carbon nanotubes, they use in thousands of tons in a variety of different applications. So personally, I think two dimensions is a little bit just because of mathematics. It just sits on this border case, and the phase transitions look different, and so it is the property of the Coulomb law in two dimensions. But in terms of materials, I think all of them are going to be used and are being used already.
All right, thank you. Yes, please, the gentleman.
Hello, Professor. So I'm Shapnadi from India, and my question is regarding another class of materials which has also come to the fore recently for its application in optoelectronic devices mainly, that is metal halide prostites. So, and also they are recently also being used in different kinds of other electronic devices as well. So how do you see this prostite competing with these 2D materials, and if someday they can come to that level of maturity? So what's your comment on them? Well,
if only, I don't think you're asking the right person. So when I mean, I really follow this hype cycle with graphene, same with perovskite and metal halide perovskites as well. I think the science there is quite exciting. What we see in metal halide perovskites, how much chances will it get in applications? It's very difficult to predict, because it's not only it doesn't only matter how good is your technology, so it also matters how good is the technology you're competing with. So we invested so much money into silicon that it's going to be very difficult to displace it. Silicon photovoltaics, it's been developing for 40 years at least, and I think it will be very difficult to compete with this technology. But I mean, we are scientists, right? So our job is to produce new knowledge and enjoy it. So and in that sense, I think perovskites are quite interesting materials.
Yeah, fully agree with that. Thank you. Well, we are having a few online questions, so maybe I'll address one of them first. I'll pop it on the screen. Do you see manufacturing of these materials, 2D graphene, to be more energy and cost intensive than conventional systems?
What are conventional systems? So the answer is I don't know. But for example, we burn a lot of hydrocarbons, and and some of them we just burn because we don't know what to do with it, right? So if you mine oil, or if you pump oil, you basically burn the supporting gas. So and you pay carbon credits for it. Instead, it's so easy to make, say, carbon nanotubes or graphene. So it would actually come at negative cost rather than it's very difficult to say how much does it cost, because it
Depends on what we compare it with, I guess. Yeah. Okay. Another popular question online seems to be asking, how do you feel getting the Nobel Prize at such an early age of, in your 30s? This could be a question that you receive quite regularly.
It's, I'm trying not to talk about this, and I really try to avoid even pronouncing the word at all. So,
that's fine then.
Difficult to again. So what I try to say to myself that so the Nobel Prize was for the initial observation of graphene and for our first experiments on it. So I said that I will never show any of those data ever again. I will only show the data for which I and the results which we get after the prize. So it's I'm not even sure what to say.
It's fine. All right, we will move on to the next question then. I forgot who came first. Maybe the lady. Yeah. Okay.
Hi, this is Catherine from the University of California, Berkeley. And as a computer scientist, my question for you was, I know you mentioned using machine learning in your work, and I guess I was kind of wondering what your thoughts on the future of these developing technologies, and in the future if it would ultimately have the possibility of replacing to some degree lab work, and what that would look like.
There is a big question about those foundational models and how much trust do you put into the AI for hypothesis creation and verification. Currently, I think it's a fantastic tool to support our work, and though the creative work comes from the scientist. Will it ever replace the scientist entirely? I mean, it can replace the lab, so that's a possibility, and I'm sure it will have its say in the design of those facilities and in the design of the scientific instruments. But how much would it have in replacing the scientist with the creative work? I don't know. I don't know what is the nature of creativity, where all the ideas are coming from. Have no idea. I mean, I usually enjoy when they come in my dreams. Can AI dream? Don't know, but I think it's a legitimate way of getting new results. So I think it's going to be used a lot. Replacing scientists, probably not.
Thank you.
Thank you. That's wonderful answers. Actually, we are running out of time. The timer has just gone off. I do have a quick question. Is that a quick one that we can entertain, perhaps?
I presume so. Thank you very much for your talk. You showed a structure that was self-folding. I thought, could you envision a structure that is even lower dimensional, where you have just the molecules and it is self-assembling and self-folding?
Right. So there are there were some cartoons and those unfolding which of the two-dimensional structures. We can control it, and there are ways how to do it. It's basically all about charging and controlling the interaction between charges between the Coulomb and controlling the direction between Coulomb and van der Waals. But so that's in theory. In practice, I showed some of the bulk structures. So they work on similar manner, but there are a few other. There are capillary forces are involved as well. So it's the charging, van der Waals and capillary.
Thank you.
Thank you. Sorry, everyone who still have questions. Maybe over tea break or something outside, we could catch Konstantin for a quick chat. Thank you, everyone, for your great attention, and thank you for giving such a wonderful lecture. Thank you.